Daniel Corucho from the Institute of Telecommunications at the University de Aveiro in Portugal, where he is a research fellow, and the title of the talk and the paper is Multiple Flow in Extended SDN Wireless Mobility.
Thank you, Wolfgang, for the kind introduction. So, good evening, everyone. I would just like to send a shout out to the other authors of the paper, namely Flávio Menezes, Carlos Guimarães, and Professor Rui Aguiar. This is briefly the outline of the presentation. Let's not last too long here. So, one of the many wonderful things about coming down here to EWU SDN is that everybody knows what SDN is. So you don't need to define it or say what it is, and we just can skip this slide. So it just leaves us all more time not to dwell on what SDN is or what it can do, but what it can actually become. And in fact, SDN is becoming quite the talk for upcoming 5G architectures. We all saw or heard Diego's response to Costa's question. So he almost destroyed my motivation slide. So but basically it positioned very well SDN as a potential or the great innovator on the network control playground. But why SDN and 5G? Why are we addressing this at all? And let me give you a small mobility point of view. So we all saw these Cisco index charts, and we all know more or less what 5G aims to do. We have all this explosive amount of devices starting to or predicted to become connected. We see video as becoming one of the most prominent types of online web traffic. And one key point here is that a large percentage of these upcoming connected devices will be mobile. So all these new network control considerations, increasing flexibility or capabilities for controlling and deploying whether virtualized resources or physical resources, they'll need to consider this because users will not remain static or still for a very long time. So if we are really aiming to have SDN as a core technology under this environment, and if this environment is going to become more and more mobile, then it makes sense to have a look at how SDN really handles mobile aspects. However, the point is that SDN was not initially conceived considering wireless environments. If you look at the OpenFlow specification and you try to check the ether types that are supported by the protocol and you try to put them in a Wi-Fi interface, you get some type of garbage identifier or whatever. So there have been some experiences. We all know, for example, different architectures highlighting that 5G will address somehow SDN in wireless means, but we haven't seen really deployments where the wireless aspects are really studied or evaluated, and this is actually where we want to contribute. We basically evaluated how SDN, namely OpenFlow, could be deployed up to the mobile terminal and used to do flow mobility in that entity. So how does this work? Basically, we can consider a mobile node, one of our smartphones, which has a Wi-Fi and a 3G or LTE interface, so dual interface entity. And the mobile phone is able to receive OpenFlow commands from OpenFlow controller somewhere in the network. So this means that, for example, this communication could be leveraged by the mobile node to send to the controller is perception of the network environment. For example, I detect these access points. My current access point is overloaded, or my current access point is reaching me with a low signal strength. Also, the endpoint terminal points of the network, for example, the access points or the 3G antennas, can also be coupled with OpenFlow support and also convey this information to the controller, saying I have currently too many wireless nodes connected to myself. And we can consider, for example, that the controller has got associated to it either directly or through some northbound or westbound interface, some kind of mobility decision entity, where it can interface with other controller or OSS, BSS entities and determine that handover should occur. So in this case, we basically consider that the flows that are running through one of the mobile nodes interface can be redirected to its other interface via OpenFlow commands. In the network nodes themselves, this of course requires also, in fact, in the mobile node first, what we did was to add open switch and a bridge attached to each one of the physical interfaces of the mobile node. To connect the bridges, we created a patch port. So what happens in practice is when we have one application that wants to send out a packet and for a already ongoing flow, the packet is always constructed or sent from the kernel towards the network interface card with the current connection MAC details, source address and destination address. But what we do is we capture that packet. We can change or modify the source and destination MAC addresses, and via flow mod commands sent from the controller, we can do forwarding of that packet from one bridge to the other and make this packet leave the mobile node through the other interface. Of course, this was an adaptation mechanism to the existing implementation of OpenFlow, which was of course not designed to run on mobile nodes. And of course, we have inherited some of the already existing mechanisms that switch, a regular OpenFlow switch and a regular OpenFlow controller have, such as the keep alive. We can talk about this, or we will talk about this later on. For the network entities, we chose to use POX for the OpenFlow controller. We developed the Python script to handle the handover solicitation, but this is in fact, although not heavily focused or not the focus of our paper, it's an important point because basically this is where you would place the handover decision intelligence. So this can either be done through an accessory module or connected through a dedicated entity somewhere else in the network. The remaining of the nodes, namely the access points, they had installed over them OpenV switch, which means that the controller can actually place network control decisions for doing management over them. Then there was the addition of or the need to add further Linux configurations over those nodes. For example, to handle ARP requests, usually it's the controller that does that on behalf of the switches. We leverage the fact that we were deploying this mechanism over Linux to have the operating system handling those ARP requests. So I think many of you were here for this morning's tutorial by Felix. You saw the video where there was, according to the availability of the bandwidth of the different links, the flows for the videos, as the demand for bandwidth was increasing, the flows were being switched in the infrastructure into links with more bandwidth. This is basically the same, except that it's being done in the wireless realm. So in this specific scenario, we have two mobile nodes which are in fact content sources. And we have a static listener node in the network. To do a parallelization on this, suppose that the static listener node is the TV station and the mobile sources are real live reporters doing a live feed of some news piece out there in the street. So this means that both mobile nodes are able to connect to two different types of access networks. So we tried to aim our mechanism design to be able to be used independently of the type of access network used. So the access points are able to be configured with a predefined load threshold, and when that threshold is crossed, they can trigger the controller to initiate an handover action and switch the flows of the mobile nodes from the affected access point into an access point with less load. To do this load monitoring in the access point, we basically measure the link capability in the wireless physical interface, and basically do an average of the latest samples, just to avoid ping-pong effect. But of course, this mechanism is not mandatory. We can try, for example, connecting into OSS or other kind of management mechanisms already existing in the network. So in terms of results, the scenario went as following. Basically, we have access point 2 already with around 8 megabit garbage flow. So let's say that the news reporter used already existing Wi-Fi network in the area to send out the news piece. But then when he got connected, since he was generating high quality video, the throughput increased in the access point. Now let's assume that the access point had the threshold configured for around 18 megabits per second, and when that threshold was crossed, which happened here when mobile node 2 also connected, the throughput raised above the threshold. So a trigger was sent to the controller, and the controller initiated the handover procedure. That handover procedure is done through the usage of a flow mod message, and it basically makes mobile node 1 move from access point 2 into access point 1. So we can immediately see that access point 1 starts to get used, and the load in access point 2 decreases. But mobile node 2 remained in access point 2, and let's assume that since it's a live feed with real-time codec, the bandwidth demand started to increase due to some kind of shift in the scene, for example. So the mobile node 2 itself started to broadcast above the 18 megabits per second threshold. So that also generates an handover trigger, and the network controller, since it knows that access point 1 already has mobile node 1 there, it shifts mobile node 2 into access point 3. So we achieve the kind of like make before break load balancing using OpenFlow protocol. We also analyzed the impact of this handover triggering opportunity detected by the access point, just to exploit the flexibility of this mechanism. And by increasing the time interval, we of course verify that we get a larger amount of time between the detection of the load and the actual reception of the handover command by the controller. With this, we were able to achieve handover times for mobile node 1 of about 14 milliseconds, and for mobile node 2, which was a little bit farther away from its original access point, of about 360 milliseconds. So yes, there are differences, and the values are a bit in extremes, but we need really to, and also especially if we compare the worst case with the existing optimizations in IP fast mobility, for example, we get these not very competitive values, but we have to take into consideration that neither OpenVSwitch or OpenFlow are done considering the application in mobile nodes. So we did not actually do any kind of optimization to the software yet, at least for this paper. So we are dealing with all these kinds of issues, namely the mobile node needs to be operating in promiscuous mode because of the two interfaces, and to do the MAC address replacement. So it means that it needs to have a look in all the packets inside its kernel. Then we have all these sorts of issues. For example, data channel and control channel being shared in the same wireless link where the other mobile node also is connected to, plus the garbage throughput. So the scenario was already a bit complex, so it didn't allow this to shine. We can see that, for example, for this sendover, since we need to send the flow mod messages to two different interfaces, it means that we have a total of 5 OpenFlow messages exchanged per handover, which means more or less 600 bytes, 80% of which are done by the mobile node, whereas the remaining 20% are the packet-in that the access point uses to indicate to the controller that an handover is necessary. We also remember that I told you that we maintain the keep alive mechanism. That is basically used for the switch to tell the controller that it's still operating. And the controller then can initiate Dijkstra to do redundancy to get back to the same point. This is not really necessary here, but it created some impact. In fact, so if we get a keep alive message every 5 seconds, we get 25 keep alives plus times 2 for the mobile node, because it's 1 for each interface. So we get around 3 kilobit of overhead in the handover experience. So in conclusion, we basically wanted to present a first study here on how OpenFlow could be used all the way up to the end nodes to support mobility-based operations such as flow mobility. We saw some of the benefits, but we also saw and already pre-identified some aspects which need to be taken in consideration if somehow SDN really wants to take a peek at the mobile world, or at least the wireless aspect of the mobile world, in an independent way of the access technology and without requiring other mobility protocols working in parallel. As future work, we are going to, of course, compare these procedures with already existing IP mobility management procedures. In fact, we have an in-house implementation of Proximal IP v6 at home, so it's going to be our first target. We are also going to analyze Lisp, try to get around handover delay, and of course try to improve Open vSwitch integration into mobile network, into mobile node devices. And I hope I gained us some time, Wolf. So thank you for your time. Questions?